Hello, this video is for the textbook lesson for Chapter 1, Lesson 7. It is titled Simplifying Expressions. Our objective in this lesson is to use the commutative, associative, and distributive properties to simplify expressions. Also, we're going to combine like terms. The vocabulary for this lesson is term, like terms, and coefficient. So who uses this? Well, triathletes can use the commutative, associative, and distributive properties to calculate overall times mentally, that is to say, do mental math. A triathlon is an endurance race that includes swimming, biking, and running. Tri, meaning three events, swimming, biking, and running. The winner is determined by adding the times for each of the three events. The commutative and associative properties of addition and multiplication allow you to rearrange an expression to simplify it. So we'll go ahead and take a look at what all that is about. Here we have a table listing the properties of addition and multiplication. These are not all the properties, they're just a couple of properties, and particularly the commutative property and the associative property. So in words for commutative property, we say that you can add numbers in any order and multiply numbers in any order. Here we have a couple of examples using numbers. Here we have 2 plus 7, and this is equal to 7 plus 2. Notice that we've just switched the position of the 2 and the 7, but they are still equal to one another, the commutative property of addition. With letters, we would say that A plus B is equal to B plus A. Also for multiplication, this holds true as well. 3 times 9 is equal to 9 times 3. 3 times 9 is 27, and 9 times 3 is 27. They both equal the same amount. Notice that the 3 and the 9 have just simply switched positions. They've changed locations. As I say, they've moved from one position to another. In letters, we would say that A times B is equal to B times A. Order does not matter for numbers and for addition, and also for multiplication. We can change the order that they come in. The associative property, in words, we would say when you are only adding or only multiplying, you can group any of the numbers together. Here's our example using numbers. We have 6 plus 8 plus 2. Notice that the order is 6, 8, and 2. And this is equal to, again, 6, 8, and 2. But the grouping is different. In the first, over here on the left side of the equation, we have 6 plus 8, where they're saying, okay, add 6 plus 8, then add 2. Well, we would get the same result if we did 8 plus 2, then added 6, right? 6 plus 8, 14, add 2 is 16. And 8 plus 2 is 10, plus 6 is still 16. In algebra, using just letters, we would say that the quantity of, notice the use of the word the quantity of to represent the parentheses, the quantity of A plus B plus C is equal to A plus the quantity of B plus C. Also in multiplication, this holds true as well. Note the order is the same on each side of the equation, 7, 4, and 5, 7, 4, and 5. However, the grouping is different. On the left, we have 7 times 4, and this equals 28, times 5 is going to be 140. And over here on the right, we have 4 times 5, which is 20. 20 times 7 is also 140. So both of them are equal to one another. It's just that first, on one side, we're multiplying 7 times 4, then multiplying by 5. And on the right side, we're doing 4 times 5, then multiplying by 7. The grouping does not matter. In using letters in algebra, we would say the quantity of A times B times C is equal to A times the quantity of B times C. Or we could say that the product of A and B times C is equal to A times the product of B and C. The word product implies, it tells us to multiply. So, student to student, here's Lorna Anderson. She goes to Pearson High School. She's talking about the commutative and the associative properties. She says, I used to get the commutative and associative properties mixed up. To remember the commutative property, she thinks of people commuting back and forth from work. When people commute, they move. I can move the numbers around without changing the value of the expression. So the key phrase is, for commutative property, whenever we go from one place to the other, we commute. Like a commuter train takes people from one place to another. So the idea of commuting is the root word idea for the word commutative. So remember, commutative, commute means to move, so we get change position. For the associative property, I think of associating with my friends. They're the group I hang out with. In math, it's about how numbers are grouped. So associative property, I've often taught this myself the exact same way, is that whenever you talk about the associative property, you might say, who do you hang out with? Who's your group of people, right? And so whenever we see that the groupings change from one side to the other, and we change the grouping, we realize that that is the associative property. Who are the numbers associating with? Are they changing friends? Do they have the same friends, etc.? Those type of things. Numbers have friends? It's interesting. So example 1, using the commutative and associative properties. So helpful hint is compatible numbers help you do math mentally. Try to make multiples of 5 or 10. They are simpler to use when multiplying. So let's look at example A. We have 4 times 9 times 25. Well, if we did 4 times 9, and what is that? 36, and then try to multiply 36 times 25, that'd be kind of hard to do mentally. But if the 4 times 25 makes 100, and all of a sudden 9 times 100 would be simple. So let's go ahead and change the position, switch the 4 and the 9 around. So they changed position, they commuted, they moved, so this is the commutative property. Now we're going to group together the 4 and the 5, so this is the associative property. The 4 is now associating with the 25. Now we can do this simple math of 4 times 25 to get 100. Let's bring down this 9. Now we can do the 9 times 100 to get 900. On example B, we have 25 plus 48 plus 75. Well, hopefully you're seeing that the 75 and the 25 would go together really nicely. So let's go ahead and change the position of the 75 and the 48. That means they're moving. They are commuting, so it is the commutative property. We just changed the order, and 48 and 75 has switched places. Now let's go ahead and group that 25 with 75 so that we can get 100. Whenever we group those together, we are associating them with one another. So 25 plus 75 is 100. Let's bring down that 48. Now 100 plus 48 equals 148. Makes it a little bit easier. So if I were to approach either of these problems and looked at them, I would probably do the exact same thing with mental math. I'd think, 25 times 4 is 100 times 9, 900. If I saw this here, I'd be like, 75, 25, 100, add 48, 148. So let's go ahead and use that strategy on a couple of these. Now I'm realizing right away, I'm seeing this 1/3. First you might think, oh, fractions, I hate fractions. But the 1/3 and the 2/3 works together real nicely. So let's do 15 and 1/3. And we're going to add that to, now let's go ahead and switch the 4 and the 1/3. So we're going to move our 4 and the 1 and 2/3. You know what I'm saying. I'm going to move that 2/3 over there, and then I'll move the 4 over here. This was, they changed position, so it's the commutative property. I'm just going to abbreviate that COMM. Now, I can go ahead and add these together. 15 plus 1 is 16, but I got 1/3 plus 2/3, that's 1, right? So the fractions together is going to make 1, plus the 1 is 2, plus 15 is going to be 17. So, and I guess I could have rewrote that. Whenever I grouped them together right there, that's the associative property. I should have wrote an extra line, but I've run out of space. Let's bring that up, plus 4, and 17 plus 4 is going to be, what is it, 21, right? On the next one, I see that, I'm not going to write this out on the lines just for the sake of time. I noticed that the 410 and the 90 would go together really well. Actually, I am going to put them together. So let's go ahead and switch 410 and 50, or let's switch 58 and 90. There we go. We're going to switch these two around, right? Going to be the commutative property. They're going to change position. 410 plus, now moving the 90 over there, moving the 58 over there, and the 2 is still there. Now this works out really well because I can group the 410 plus the 90 and the 58 plus the 2. This is the associative property, right? So first step was commutative property. They change positions. The second step is group them. That's the associative property. Now I've got something real easy here. 410 plus 90, well, that's 500, right? And the 58 plus 2, well, that's 60. And 500 plus 60 is 560. On the next one over here, 1/2 times 7 times 8. Well, the multiplication here, think of that as the word of. whenever we see multiplying, we can think in our head, oh, the word of. Well, 1/2 of 7 times 8. Well, 1/2 of 7 won't be as easy as 1/2 of 8. So let's do this. Let's do 1/2 times, now let's switch the position of the 7 and the 8 and do 8 times 7. Now we could go ahead and group these together. That would be associative property. 1/2 of 8 is 4. Now let's bring down the 7 and not another 4. Let's bring down the 7, and 7 times 4 is 28. So see how in our head we may not even realize it if we're doing that. If you were to see this and you just kind of thought, okay, 1/2 times 7 times 8, let's take half of 8. I get 4. 4 times 7 is 28. You really don't even realize that you're applying properties of commutative property and the associative property in order to do that. Technically, you're also doing something called the closure property, but that's not in this lesson. So, the distributive property is used with addition to simplify expressions. So, distributive property, what's that all about? Well, you can multiply a number by a sum or multiply each addend by the same number, then add. The result is the same. Now, that might sound a little confusing there, and the words kind of run together. But let's look at that example. So I have 3 times 4 plus 8. Now, if I went ahead and did the 4 plus 8, I would get a total of 12. So let's go do 12 in there. And then do 3 times 12, that's 36. But let's see if we try something else. If we go ahead and distribute the 3 times the 4, like we see there, apply the 3 to the times 4. And then we also apply that to the positive 8, so that's going to be a plus. And we're going to have 3 times 8. Now, 3 times 4 is 12, plus 3 times 8 is 24, and 12 plus 24 is the exact same 36. So you can see here that the distributive property does hold true. Instead of adding these together and then multiplying by 3, instead we can distribute the 3 to the 4 and the 3 to the 8. Let's talk about distributive property. Long ago, it's been a while, I used to deliver newspapers, N-E-W, we'll just do newspapers. And I had to send that newspaper to several different houses. So I'll draw some houses here real quick. Not much of an artist, but a pretty good math teacher, I hope. So the idea was I was in the business of distributing newspapers, and the same newspaper had to go to each house. So I would deliver the same newspaper to each house. And just like I distributed the same paper to each house, likewise, the number that's being multiplied times whatever the quantity is here gets distributed into each of the terms that's inside of the parentheses. We'll talk about what terms are in a moment. So we would distribute the 3 to the 4 and the 3 to the 8. And this does mean multiply. So that would be the operation. That's why we have 3 times 4. And over here we have 3 times 8. And this is a plus sign because that's a positive 8. And this is a positive 3. Now in algebra we would say that A times the quantity of B plus C, or A times the sum of B and C, is equal to the sum of A times B and A times C, or AB plus AC. So the distributive property also works with subtraction because subtraction is the same as adding the opposite. So let's take a look at that example here. Whenever they say that subtraction is the same as adding the opposite, let's do 5 minus 2, right? What's 5 minus 2? Well, hopefully you say 3, right? Well, I can do the same. I can just add the opposite. I take 5, change the sign to addition, take the opposite of 2 and get negative 2. Now what's 5 plus a negative 2? It's still 3. So subtracting, like it says, subtraction is the same as adding the opposite. So subtraction, 5 minus 2, is the same as adding the opposite. That is to say 5 plus negative 2. And that's a little trick that I use quite often. I use this one a lot. So in this case, what we're talking about here is if we have some number, and let's just go ahead, let's use the 3 here. Let's go ahead and get rid of my, really starting to ramble now, aren't you, Mr. T? But this is good, this is some good stuff. I want to go ahead, and the textbook doesn't really have it here. They mention it, but I want to go ahead and point it out. Let's say we had 3 times the quantity of 4 minus 8. Let's say that was minus instead. So we would have 3 times 4. It would be 3 times 4. and not 44, but 3 times 4. And then I could put a plus sign if I wanted to, and do 3 times, actually go ahead, let's leave it as a negative there. So 3 times 8 is, then we're going to have 3 times 8. And so then we could do the 3 times 4, you get 12, minus 3 times 8 is, what is that, 24, right? And 12 minus 24 is the same as 12 plus a negative 24. Here I go again, change the sign, do the opposite. And since I am adding a positive and a negative number together, I could actually subtract 24 minus 12 is 12. And since 24 has a greater absolute value than 12, I'm going to use the same sign as 24 has, and that would be negative 12. So it could be subtraction inside there. That's the point they're making. And I probably just spent about an extra 4 minutes explaining that. I could have done a better job, I suppose. All right, example 2, using the distributive property with mental math. So break the greater factor into a sum that contains multiple of 10. And we'll see if that comes in handy here. So write each product using the distributive property, then simplify. So in example A, we have 15 times 103. Now, I could probably do that mentally, but honestly, if I did that mentally, I'd do exactly what they're doing here. They're going to take 103, and they realize that 103 is the same as 100 plus 3. So let's write this out as 15 times 100 plus 3. It's the same thing as 15 times 103, right? Now let's go ahead and do 15 times 100. We see that here. And 15 times 3. We see that there. Now, 15 times 100 is pretty easy, right? It's just 15 with 2 zeros on the end, 1500. And 15 times 3 is 45. Now we can do 1500 plus 45 is 1545. I should just say 1545. If you're being a stickler, 1545 would be 15.45. But that's another lesson on the proper use of the word and whenever it comes to mathematics. If you hear and, should be where the ones place ends and the decimal hits, and then everything after that is tenths and 100ths and those type of things. So to be exact, it is 1545. Take the word and out. In example B, 6 times 19. Let's see, if I did this mentally, honestly, I would probably do that as 60 plus 54 for 114, right? And I would have done that using the same distributive property. I would have done 6 times the quantity of 10 plus 9 is the way I would have done this in my head. And I would have got 6 times 10 plus 6 times 9. And then I would have thought, okay, this is 60 and this is 54. And honestly, I would have then in my head thought of the 54, I would have thought 60. In my head, I would have thought 60 plus, and I would have split the 54 into 50 plus 4, because I know that 6 and 5 is 11, so that would be 110, and then the 4, and then end up at 114. Now, I would do that in my head a heck of a lot quicker than I could write it out. But the textbook here is going to take a different route, probably because they want to show that you can use subtraction here. So instead of 19, they're going to rewrite 19 as 20 minus 1, and that works out well. For you, you might even think that the way the textbook does it's a little bit easier than the way that I chose to do it over here. So 6 times 20 we have here, 6 times negative 1, or this is actually, we'll just call it 6 times 1. I'm so used to think of it that way, but that's actually plus a negative 1, because, Mr. T, what the heck are you talking about? 20 minus 1 is equal to 20 plus negative 1. So I think of this as a negative 1. That's going to be a negative 6, etc. I just kind of like to keep, I would rather add integers than I would subtract whole numbers. So we shall move along. So 6 times 20 is 120. 6 times 1 is 6. We still have the subtraction here. 20 minus 6 is 120 minus 6 is 114. So that's how they would get to that there. Let's go ahead and apply that here to our check it out. Let's rewrite 52 as, let's see, I think 50 plus 2 is probably what they want us to do would be best. So I would have 9 times 50 and add that to 9 times 2. 9 times 50 is 450 because 9 times 5 is 45, throw the 0 on the end. And add to that 9 times 2 is 18. So whenever I add those together, I would get 450, 468. And again, I could have done that mentally, didn't have to write it all out. But if I don't write it out, you can't see my mental math, right? The teacher says you got to show your work. Let's do 12 times, let's think of this as 100, right? But that's actually 100 minus 2. Let's go that route. So 12 times 100, and then we'll distribute that over to minus 12 times 2. 12 times 100 is 1200, minus, and 12 times 2 is 24. And then 1200 minus 24 is going to be 1176. 1176. And in my head, I actually did 1200 minus 20 would be 1180 minus 4 more. So I actually did 1200 minus 20 minus 4. Thinking of 20 is 20 plus, 24 is 20 plus 4. And then finally, 7 times 34. I would probably do this one as 7 times 30 plus 4. That would probably be the way to do it. So I have 7 times 30 plus 7 times 4. Distribute that 7 into the 30 and the 4. This is going to be 210, right? 7 times 3 is 21. Throw the 0 on the end. Plus, and 7 times 4 is, what is that, 28? Right. And now I'm going to think 238. That's actually, I'm going to think of 210 plus 20 is 230 plus the 8 is 238. Interesting. That's my old tractor trailer number whenever I was a truck driver. Or Patashnik. Tractor 238. It's also the house number in the movie, the one with Clint Eastwood, Gran Torino. Yeah, Gran Torino. His house number is 238. I had that tractor number for so long, every time 238 shows up someplace, I'm like, hey, that's my tractor number. All right, we're going to move on and talk about terms, like terms, coefficients, and those type of things. So the terms of an expression are the parts to be added or subtracted. So these parts that being added or subtracted, anything that's separated by an addition or subtraction sign, these are called terms. Now, like terms are terms that contain the same variables raised to the same power. So here I have an x and an x. They're both raised to the first power. You don't actually see it there, but technically I could go ahead and throw that a 1 there. So these are both raised to the first power. And so they are the same variable raised to the same power. Therefore, these two are like terms because they have the same variable raised to the same power. Constants are also like terms. Constant here is a number that does not have a variable. All right. And it's constant because it's not going to change. This value of 2 is always going to be 2. But 3x, it could change all depending upon what the value of x is. If x were 1, then this has a value of 3. If x were 4, then this has a value of 12. So the value can change all depending upon what the value of x is. However, a constant, a term without a variable, it's just stuck at that value. So it is constantly going to be 2. Notice that's the word constant. That's why we call them constants, because they're always going to constantly be the same value. Next, a coefficient is a number that is multiplied by a variable, such as 1 or 3. Like terms can have different coefficients, such as here we have they are not like terms. Notice here, these are not like terms. Same variable, different exponents. But these two are like terms, but notice that their coefficients are different. So like terms can have different coefficients. A variable written without a coefficient has a coefficient of 1, and they show that here. X squared has the 1 out in front of it. Now, you could rewrite this as x squared plus 3x, and it would still be the same value, because even though you don't see it there, it is implied that there is a 1 there in front of it. And this is important to understand, that every variable has a coefficient. It just so happens to be, if it's a 1, it's the invisible one. It's there, we just don't see it. You get it? The invisible one? Like, it's never mind. Goes over much better in the classroom. So, let's see. Also, I want to add on here, I like to call these leading coefficients, because in mathematics, we always want to write it as 3x. We wouldn't want to write x3. We want the coefficients to go before the variables. So in this case, I always like to refer to them as the leading coefficient. And I'll just use CO for coefficient. I'm also going to switch back to red. All right, so using distributive property can help you combine like terms. You can factor out the common factor to simplify the expression. So here we have 7x squared minus 4x squared. Notice that they are both the same variable, x. They're both raised to the same power, power of 2. So therefore, these two are indeed like terms. So we can factor out that like term of x squared. So we kind of just pull it out of both the 7x squared and out of the negative 4x squared. And what we would have left, if we pull that square out, it ends up over here. And then in parentheses, what we have left is the 7 minus 4. Notice that we've taken it out. Now, you could always double check this. If you were to distribute that back in, you would have x squared times 7, x squared times 7, and x squared times minus 4, x squared times minus 4, or negative 4x squared. Now let's go ahead and do 7 minus 4. We get 3, and we can simplify that to 3x squared. Notice that you can combine like terms by adding or subtracting the coefficients and keeping the variables and exponents the same. So here, the variable x and the exponents 2, they stay the same in the answer. We see it right here with x squared, and all we did was just 7 minus 4. Now, whenever it comes to combining like terms, I always like to use the analogy of it's like adding or subtracting elephants or giraffes, right? If you had 7x squared minus 4x squared might seem a little confusing to somebody. But if I ask you, what is 7 elephants minus 4 elephants? You'd be like, oh, it's 3 elephants. So 7x squares minus 4x squares is 3x squares. So just make sure that they are like terms. Variables are the same, and the exponents are the same. Combining like terms, simplify each expression by combining like terms. So here we have 12x plus 30x. So I have 12 x's and 30 x's. Think of it this way, 12 elephants plus 30 elephants equals 42 elephants. So we can go ahead and combine those together because they are indeed like terms. They're both the variable x. Their exponent is the value of 1, even though we don't see it. X is the same as x to the first. So they are indeed like terms, so we can combine 12 plus 30 to get 42. On the next one, example B, we have 6.8y squared minus y squared. Well, let's go ahead and remember every coefficient or every variable has a leading coefficient, but if it's 1, you just can't see it. It's the invisible one. So let's go ahead and actually put the 1 there so that we remember it's there. So 6.8 minus 1 is 5.8. 5.8 what? 5.8y squares. They are indeed the same variable, y. They have the same exponent, so that checks out. So the same variable, same exponent, they're like terms. So we can do the 6.8 minus 1 to get 5.8. What about 4n plus 11n squared? Well, as you can see here, it says they're not like terms. And indeed they are not, because where they both are in terms of n, the first one here is n to the first, but the second one is n to the second. So the variables match, but the exponents don't match. So they indeed are not like terms. They have to be the same variable raised to the same power in order to combine them. So let's go ahead and simplify each expression by combining like terms. First of all, are they like terms? Well, p to the first power, right? They're both p to the first. So I can do 68 plus 84. That's going to be 84, 94 plus another 6 is going to be 100. 100p. On this one here, terms of t, so we're good to go there. So we need to take negative 20, and we're going to go ahead and subtract from that 8.5. And so 20, I really don't like this one. Let's go ahead and do this differently. And whenever I say do it differently, it's because I don't like 20 minus 8.5. I like 20, negative 20, plus a negative 8.5. All of a sudden, this gets a lot easier. It's negative plus negative, so it's going to get even more negative. So that's going to be negative 28.5. And let's throw that t back on there. And then finally, the last one, I have m and m, but I have an exponent of 2 and an exponent of 3. Therefore, these are not like terms. The variable is the same, but the exponents are not the same. So they are not like terms. I cannot combine them. All right. This reminds me of a college class I took. It's in geometry. Whenever we do something like this, we call it a proof. I had a class where they would give us one thing. they'd say, here's one expression, here it is simplified, now how do you get there? And you had to list every single step, and that's exactly what they're doing here. So simplify algebraic expressions, simplify 2 times the quantity of x plus 6 plus 3x. Justify each step with an operation or a property. This is exactly what we had to do in college, is we would start with, and it wasn't quite this short, it was much more difficult than this. And actually it only used variables. We used no numbers, except for the number 2 and the number 1, because you had to use that to represent odd numbers. So at any rate. So here we first have the distributive property. In the first step we're going to 2 times x and 2 times 6. And we're going to bring down the 3x, so that's the distributive property. Next step is to go ahead and multiply 2 times x equals 2x, 2 times 6 equals 12. The next thing we want to do is we want to get the x's next to each other, so we're going to switch the place. We're going to switch 3x and 12, so things are moving, right? And so they change position, so that's the commutative property. Now I'm going to go ahead and group the 2x and the 3x together with these parentheses. That is the associative property. Remember, associative property is grouping. You see parentheses show up, it's grouping, it's associative property. Now we're going to go ahead and combine like terms. 2x's plus 3x's is 5x's. And at this point, we can't simplify any further, and this is the end, so we're at 5x plus 12. On this one here, simplify each expression. We're only going to do one of those because I'm looking at the time, probably because I rattled so much on the other stuff that I'm crazy excited about. And so I'll go ahead and we'll just do the problem here, plus x. And then let's go ahead and grab all of this because I want to be able to have a little more room to work with it. So we're going to put it up right over here. And I want to be able to have space to write each explanation here. So I'm thinking that, first of all, I might want to go ahead and group. It means I got to I have to rewrite all this. Negative 12x plus 5x. We're going to group these, and we'll bring down the plus 3a and the plus x. And this was grouping, so this is the associative property. Next, we're going to go ahead and add these together, right? Negative 12 plus 5. Negative 12 plus 5 is the same as negative 12. Well, actually, we'll stick with that. So 12 minus 5 is 7. And negative 12 has greater absolute value, so this is going to be negative. So negative 7x. And let's bring down the plus 3a plus x. This is multiply. And oh, I got some x's here. So next thing I need to do, let's get the x's next to each other. So we're going to go ahead and switch the place of the x and the 3a. So I did some moving. They switch places, so things that move, that's commutative property. Now I have negative 7x. See how this could really work out to be a really long process. I got to group these. That's associative property. Now, this was multiplying, this was adding. There we go. And now I have to add those together. Remember, there is a 1 right here in front of that. So negative 7 plus 1 is a negative 6. I get negative 6x plus 3a, and that was from adding. And finally, we're at its simplified form, and it took, what, 1, 2, 3, 4, 5 lines to get there. All right. So here we are at our exercises. I don't know if I'm going to spend too much time here. Vocabulary. The blank property states the following. The quantity of a plus b plus c is equal to a plus the quantity of b plus c. So the first thing I always like to check is, did the order change? I see parentheses here. I'm going to pretend I don't see it. A, B, C, A, B, C. So order does not change. So the commutative property is not it. It's definitely not the distributive property over here. Nothing's getting distributed. It is indeed the associative property, and notice that A is grouped with B, but over here B is grouped with C. So it's just the changing of the groupings. Groupings refer to the associative property. Let's simplify each expression. On this one here, I would take the 1/3 and put it with I'd take this 1/3, put it with the 21. 1/3 of 21 is 7. And then I would multiply it times 8 to get 56. If you ever have a hard time remembering 7 times 8 is 56, think of it this way. 56 equals 7 times 8 5, 6, 7, 8. That's my memory device for it. All right, let's look at let's try the one with the fractions here. I've got a half and I've got a half here. I will put the 2 and the half and the 1 and a half together, and the 16 together and the 4 together. The 16 and the 4 together is going to give me what, 20, right? And then 2 plus 1 is 3, plus the 2 halves is going to put me at 4. That's going to equal 24. So I know I'm not quite doing this the way that I should. I think I would multiply maybe the 50 and the 20 together. 5 times 2 is 10. Throw a couple zeros on there, and then multiply times the 118. And this is going to equal 118 with, what, 3 zeros on the end. 118,000. That's the way I would handle those. Let's look at a couple of them here. 14. I'm looking at this one here, number 8. 14 times 1,002. I would separate that in 14 times 1,000 plus 2. And then I would get 14 times 1,000 and plus 14 times 2. And this would be 14 with 3 zeros on the end, plus 28, which would give me 14,028. All right, so there's 8 on that one there. And then let's see about simplify each expression by combining like terms. Let's look at ones that we can combine and then one that we can't. So here we have terms of x. They're both to the first power. So 6 plus 10 is 16. So we'd have 16x. On the other one here, number 18, this is x to the second. This is x to the first. So whereas the variable's the same, the exponents are not. So those are not like terms. We cannot combine those. 35x and minus 15x. They're both in terms of x. They're both to the first power. So we can combine these. 35 minus 15 is 20. 20 what? 20x. And then from there, we'll go ahead and go on with that. And we won't even look at number 4. We don't have the space to write all that out. So that pretty much completes my presentation for textbook chapter 1, lesson 7, simplifying expressions. And thank you.